Yo, I hope again that you guys are all doing well, and I really sincerely mean it. I hope you're doing well because if you're doing well, you're more likely to like the video, you're more likely to share it, you're more likely to finish uh, watching the whole video. Just joking, let me not be so shallow. I really do hope you are doing well. This is going to be part two of probability. And again, we coined a phrase, or we made one phrase that really takes us through the essence of what probability is. This is something we did in the last lesson, amongst other things. So we said that probability is how likely it is for something to happen. I've also added the unlikely it is for something to happen. We've talked about the tangible things like outcomes, union, intersection, mutually exclusive events, complementary events, and so on and so forth. We've done it by using illustrations on a Venn diagram to show how intersection and union look like. We've done these small examples that I made up on the spot. So, one thing, and I hope that you're going to be sticking with me on this journey of me attempting to help you guys achieve your academic goals, whether it's by explaining to you a question or by solving questions for you. One thing you're going to learn about me is that I just do things on the spot. These things are hardly prepared for. So you could say I'm doing a constant unprepared speech. I'm just saying what I think. So sometimes my examples might not add up. They might not give you round natural numbers or counting numbers. You might get a decimal or two here or there. I just ask you to bear with me. Maybe I should start preparing for lessons, start preparing for these videos, but I feel like that would take something away from the realness of what I'm trying to establish with people who watch my videos. Anyway, despite all that, last lesson we talked about the most important things being the mutually exclusive events, which are the type of events that cannot happen at the same time, and complementary events, which are the type of events that focus on everything else except the one event. And we used this Venn diagram example where we said, what's the complement of not MTN? Or what's the complement of people who use MTN? And we said that would be the people who use Telkom, Vodacom, and Cell C. Or we say, you can talk about it in another way, what's the probability of not MTN? And that would be the same thing. It would be the numbers 5, 7, and 6, or the people who use Telkom only, Vodacom, and Cell C. You're looking at that Venn diagram. We also talked about mutually exclusive events by saying that when they are added together, they equal 1. And we said that the probability of both events happening at the same time, like A and B, that is 0. Now let's move over to another thing to finish off concepts, and then we're going to look at formulae and then start solving questions, God willing. So dependent and independent events. If you are doing maths pure and you also do physical sciences, these terms are not alien to you. You've probably seen these words before. Maybe these are questions that you dread, or maybe these are questions that you are quite used to and fond of, where they ask you for independent variable, for a dependent variable, for the controlled. So you probably have seen this before. If you're the type of student that does pure maths with no science subjects, well, it's okay. I'll be able to explain it to you. And if you can tie this concept to a word that you are used to, or a concept that you're used to, then it makes everything a lot easier. So a dependent event is the type of event that is dependent on the event that happened before. Let me make that more simple. You can imagine that we have two events that are happening. So we can say maybe you're going to toss a coin twice. So these events can happen, it can be the same events happening several times. So maybe I'm going to be tossing a coin, but I'm going to do it repetitively. So maybe like 2 or 3 times. Or it can be another example like this. Maybe I'm going to toss a coin and roll a dice or roll a die. So it can be two separate distinct events or the same event but done numerous amount of times. So this is for both independent and dependent events. A dependent event, is the type of event where we say, look, maybe by me tossing the coin the first time, it will affect what I get the second time. Or let me give a better example, because tossing a coin is not actually dependent. Maybe you might say, okay, so you're going to ask someone for something, for a favor. Maybe you want them to borrow you a calculator. You forgot your calculator in the at home, or maybe you don't have one, whatever. So we are going to talk about the probability of you, firstly, how you greet somebody, and then how they respond to your request for the calculator. So we say if someone says please, what's the probability of someone saying please? So it's 1 out of 2, for example. So it's either they say please or they don't say please. So the probability of saying please is 1 out of 2. Then we'd say, okay, if someone says please, the person who's going to borrow the calculator, the probability of them borrowing the calculator is more likely. So we can say that that's a dependent event because the second event depends or is influenced by the first event. And that's exactly how we're going to define dependent events. So dependent events are the type of events where the second event is influenced by the first. Now, if the second event is not influenced by the first, which are these two examples that I've actually given here, these two examples here are both independent events, in that when I'm tossing the coin the second time, I still have the same amount of outcomes and I still have the same probability. So if I toss a coin the first time, my probability of it landing maybe on tails is 1 over 2. If I toss a coin a second time, the probability of landing on heads is 1 over 2. So we know that probability is made up of two things, especially when we're talking about its rational format. We have the total outcomes here at the bottom, and we have the event outcome here at the top in the numerator. So we say that the total outcomes remains the same, and the event outcome, maybe it can change, but the total outcome remaining the same, that's what determines if something is a dependent or independent event. So to be able to distinguish or to make distinct what is a dependent event and what is an independent event, you will see it with the total outcomes. Let me give a more tangible example for a dependent event, because I don't think that one for the asking for calculators is as great as an analogy as it sounded in my head. So we can think of a basket or a bag. Let's just say this is our basket. And in this basket, we have balls of different colors and different numbers. So in this example here, I will attempt to explain the difference, the real difference. If you haven't got it already, I'm sure most of you are quite sharp, but if you haven't got it, I'll give you leeway because I just didn't do a good job of explaining it. This one will do a better job of explaining it. So we have these balls in a bag and we mix them up and we pick one of them out at random. So in total over here we have 3, 5, 9 balls in this bag of different colors. And if I had to ask you, what's the probability of someone picking a black ball? Well, you would say we have 5 black balls and a total of 9 in total. So we say that once you take out this black ball, once you've picked a black ball, one of the 5 or 5 out of the 9, you put it back inside. So you picked a black ball, for example, and once you took it out, you put it back into the bucket or into the basket. Then I ask you again, what's the probability of you picking black on the second try? So we'll say this is on the second try. It would be exactly the same as the first try, 5/9. Now it's not, it could be because we are replacing it. Actually, that is the actual practical reason. But the mathematical reason is because the outcome is not changing. The total outcomes is not changing. And the probability, the whole probability itself is not changing. But especially the denominator, the total outcomes. So if the total outcome does not change, because of the way this scenario panned out, we kept on putting the balls back inside after we've picked them, well, we say that this is a dependent event, or an independent event, sorry, because the first doesn't affect the second. The second is not influenced by the first event. So me picking a black ball the second time is not influenced by me picking a black ball the first time, because the outcomes or the total amount of balls remain the same. How would this change if we didn't replace the ball after picking it? So again, the first one would be the same. We have a total of 9 balls, and the probability of picking a black ball, they are 5/9, so 5/9. However, this time, if we pick a black ball, we don't replace it. Now you can see that the second, or the denominator, or the total outcomes is going to be 8. And this time you can pick 4/8. So we can see that the total outcomes are changing. It changed from 9 to 8. So this is going to be an independent event. If we even talk about other colors, like the probability of you picking pink, this would still hold true. It doesn't only have to be black on the second try, obviously, I mean. So on the second try, it would again be 2/8. So we would say the probability of you picking black first and then picking pink, and you don't replace the balls once you've taken them out, are those independent or dependent events? You'd say, look, that is a dependent event because the second event is influenced by the first. The probability of the second event is influenced by the first. So that is dependent and independent events. Now, with all of these examples that I've shown you how to determine them by reading a question, because the questions are normally given to you with a small extract to explain the situation. So I've given you the tools to be able to identify just by reading a question. Is this question, are these events dependent or independent? Are these events mutually exclusive? And normally it is only those two, and you can see that's why I put these distinguishing marks. These two are the ones that you have to prove. They have a burden of proof upon them. You have to show, look, this thing is dependent, this thing is independent, either from what I've read from the extract, which shows it to be dependent, either because I can see that the outcomes are changing, or you can say that they are independent or dependent or mutually exclusive or not mutually exclusive by using a calculation. Now this is a nice segue. I like how I transition to the next page, which is the formulae. The formulae for different things in probability. So for any two events, you will always use this formula of saying, let me use another type of pen. The probability of A or B happening is equal to the probability of A. And because we said O always has a plus the probability of B minus the probability of A and B. Now remember once again, why does this thing look like this? Okay, you know what? I think we have some time. I'll get into why it is like this. When we defined union, we said union can be written as A or B, and it's that or means a plus. And it says, we said here, or I wrote here, that it means when both events occur or at least one occurs. And we showed in the Venn diagram, this is how or would look like. So we are saying that it's this and this and this, but we are saying this and this minus this. Why do we say minus the intersection point? Because the intersection point is for people who do both. While if I talk about people who do A, I would include this as well. So we say, if we looked at that Venn diagram example before, we would say that the people who use MTN are 15. And if I say the people who use MTN are 15, I'm including the people who only use MTN and the people who use MTN and Telkom. If we look at the people who use Telkom, I'm just saying use Telkom. I'm not saying Telkom only. Remember that qualifier changes everything. So if I say the people who use Telkom, it's going to be 8 people. 8 people use Telkom. There are 3 that use Telkom and MTN, but there are 5 who only use Telkom. So when we say A or B, that formula that I've written down here, we are saying that people who use A, which is 15, for example, people who use B, which is 8, minus the people who use both. Because the people who use both use this and use this as well. If you don't understand that, you don't need to understand it. But if you do, it's nice. It's something that you can use to show off. Look, I like it when you learn something. If you learn something from me, if God blessed you with learning something from me, or God blesses me with you guys learning something from me, which is also a nice thing. I like it when people, I help people academically, not in everything. But if you get something from this lesson, and it's a new topic for some of you grade 12s, go ahead and show off, man. Show off in class, flex your academic muscles, flex your brain muscles or whatever, and show people. You just put your hand up, sir. I know why it's like that. If they ask why is the formula like that, oh, what's the formula for any 2 events? You say, look, sir, it look like this. I'll tell you how it's done. Even take the marker from your teacher, ma'am or sir. Say, sir, you can sit down, or ma'am, just sit down. I'm going to show you how it's done. Obviously, I'm not condoning such disrespect. I'm just saying. Obviously, I'm exaggerating. I'm just saying you could do that. Let's carry on now with the next formula. We say there is an adjustment to this formula if the events A or B are mutually exclusive. Again, what does mutually exclusive mean? It means these events cannot happen at the same time. So we know if these events cannot happen at the same time, that the probability of A and B is equal to 0. So that would mean we do an adjustment to this formula that we've just written. Now this is just 0. So how would it look now? Obviously, it's going to be P, A or B is equal to PA plus PB, because there's no intersection point anymore. Remember, when things are mutually exclusive, as I've done before, over here, there is no intersection point. Let's carry on now. For complementary events, for the complement of B, for example, we write down the formula like this, and we've already done it. We can say P not B, or you can write it down in another format by say PB with that apostrophe kind of thing at the top. That is equal to 1 minus PB. Why? Yes, 1 minus PB. Why do we say 1 minus PB? The reason that we say 1 minus PB is for the fact that, let me write it down here, for the fact that mutually exclusive events are normally complementary events. We said that complementary events are not that. So we focus on one thing and we say, what's not that? It would be everything else except that. So we said, if we look at that set of C, if you go back to the previous video, 1, 2, 3, 4, 5, and 6, those numbers. And we say, what's the probability of picking a odd number? You'd say 3 over 6. The total amount of numbers being 6. We say, what's the complement of odd? It would be even. What's the complement of even? Odd. If we add both of those mutually exclusive events to each other, those mutually exclusive events to each other, they are going to equal 1. So that's why we start from here. We say, okay, the probability of B plus the probability of A, these are complementary events or mutually exclusive events, is equal to 1. So you say, okay, if I take this to this side, is going to be 1 minus PA. So PB is equal to 1 minus PA. And we know that PA is another way of saying PB, or the complement of PB. So the complement of PB is PA. We said the complement of odd is even. So you can think of A as even, B as odd. So 1 minus the probability of something being even is odd. So you can think of PB, the complement of PB being PA. So 1 minus PB, that's the same thing. I hope this makes sense to you. It can obviously be adjusted in the other way as well. So you can write it down like this as well. PB is equal to 1 minus this. If you don't want to understand the intricacies, the proofs and how it came there, maybe you're not the type of person to get deep into stuff, just look at the formula, you deal with the formula. Remember, all of this stuff will be at the back of your page, at the back of your exam script. For independent events, now for independent events and independent events, I'm going to show you a formula that not only calculates it, but it's also used to determine if something is independent or something is dependent. Look at this spelling error, yo. I should be ashamed of myself. Independent, not independent. Sorry, guys. I have to fix that up. Independent events. So as I was saying, that independent events are, we know the definition for them, but I'm saying that these formulas can be used to also prove if something is an independent event. Remember, I said before that you can use it by calculation. You can use calculation to determine if something's independent or dependent, and this is the calculation method. Or you can just read it and determine, look, does the second event, is it really influenced by the first? If you come to the conclusion that no, then it's independent. If you come to the conclusion that the second event is influenced by the first one, then you can use your logic and say, look, this one is dependent, it's influenced. So if we have PA and B, then we are going to say that PA times PB. Remember, we said that AND is a keyword that means or implies multiplication. And then for dependent events, obviously, it would be PA and B is not equal to PA multiplied by PB. So as I said before, these things can be used to calculate something. So maybe if they want you to calculate PA and B, or they want you to calculate PA, but they give you this and they give you this, or whatever seems to be the case. You can use it to calculate it, or they can give you the values for you to prove, is this event dependent or independent? So you can also use it to determine I'm going to use the word dependency. I don't even know if that's a word, but I'm just going to be stubborn and say that's a word, if it's dependent or independent. Let's now move on to questions. We've covered everything here. We are going to use these formulae and use the knowledge that we've learned of our concepts to be able to discern the questions, if it's exclusive, mutually exclusive, if it's not, if it's dependent, if it's independent, and how to find different things. This is a past paper question that's downloaded from stanmorephysics.com. It's not a sponsored video. I wish it was sponsored. But it's free past papers. You can use this resource here, stanmorephysics.com, to, go there, get past papers. They normally update the database from time to time. Sometimes it takes a bit long, but they are very reliable. You could go there and get past papers as well. And from there, you can email me your questions and I'll answer them whenever I can, obviously within a appropriate time period. So let's start with question 11.1. Events A and B are mutually exclusive. Here's the next page here. We're going to look at it in detail and break down the question. So we have two events, And the way that this question has described these events is that they are mutually exclusive. What comes to mind when we see that? We see firstly that it cannot happen at the same time. So what does that mean mathematically or algebraically? How would we depict that it cannot happen at the same time? We know that if it cannot happen at the same time, again, we're talking about mutually exclusive. We say if it cannot happen at the same time, then PA and B, these two events that we are talking about, that's equal to 0. And by default, we're always going to use this formula. We are going to use PA or B is equal to PA plus PB minus PA and B. But we know that this is already 0. So before we've started the question, just this two words, just this phrase, mutually exclusive, it already gives us a lot of information. We know we are going to use this formula, and we know that something in the formula is going to be equal to 0, just from those two words. The next pieces of information that are given to us, it says that PB is equal to 2 times PA. So this is a type of relation. You can imagine, and I'm just going to give an example for this. It's not really how it is. We might find it to be different. If we find out that PB is equal to 0.1, or rather, let me do it the other way around. If we find out that PA is equal to 0.1, that would mean that PB is equal to 2 times 0.1 or 2 times 0.1, 0.2. So that's all that it is. It's just giving us information. You can also take this, whenever you get a relation like this, take this as the first equation, or equation 1. The next piece of information given to us is PA or B is equal to 0.57. So this is something that we might need to. I'm going to be quite straightforward. We are going to plug it into this formula that we have here. So let's start with this question. 11.1. So as I said before, we're going to use this formula because it is mutually exclusive and because this is the default formula for probability. So PA or B is equal to PA. You write down the formula so that you can get a mark from this, if any. I don't know if you do. Sometimes you do, sometimes you don't. It really depends on the marking guidelines for your exam, but always make sure to write it down. You don't lose anything by writing it down. So PA or B, whatever, this is what we have. Now, after that, we have said that this is going to be equal to 0. So we're obviously going to be cancelling out this guy. What have we been given? We've been given information about PA or B. This is 0.57. And we've also been given information about PB's relation to PA, which was our first formula. So we can see wherever we see PB, we will plug in 2 times PA. So we see PB over here. We are going to substitute our equation 1 here, or the value of PB in terms of PA. So 2 times PA. And then this is minus 0. I will just leave it out. Now this is quite easy to see. Now we can start by finding the value of the probability of event A or PA. 3PA, you take 3 from both sides, and we find that the probability of event A happening is going to be equal to 0.19. So we have 0.19, and that's the value of PA. Is the job done? As Kobe says, job's not done. We still have to find out the value of PB. Now, to find out the value of PB, this resembles the methodology or the method that you use to find simultaneous equations, x and y. We are going to take what we found and substitute it back into the original first formula. So I'm going to write down here the steps that I've done. I haven't done this. I'm going to say sub equation 1 into this formula. So that was the first step. And then substitute the value of PA into equation 1. So we substitute it back into equation 1 so that we can find the value of PB. It is going to be PB is equal to 2 times 0.19. And so PB is going to be equal to 0.38. So this is our final answer. Let's look at one more question. Well, this one I got, it says compiled by Navan Mudali. Well, I'll say thank you to Navan Mudali for compiling this. I'll put the link to this probability questions and solutions paper in the description below. It's this lovely person, Navan Mudali. She put all together most of the questions that she could find, or he, I don't know, of probability. So questions and solutions for the different type of questions that will occur. Now the type of questions, just to give you a breakdown, are going to be Venn diagrams, if any. So you either get a Venn diagram or a tree diagram. These are things you have to know, and we're going to cover that later. You have a question to deal with mutually exclusive events or independent and dependent events, like what we've just solved now. And another question to do with combinations, repetitions, so on and so forth, especially for things like seating arrangements, password combinations, so on and so forth. So we're going to do that next time in our next video. I hope to finish probability by the next video by just going over questions. So we're going to do question 4.2 because 4.2 addresses the topic at hand. It says here we have a smoke detector system in a large warehouse that uses two devices, A and B. If smoke is present, the probability that it would be detected by device A is 0.95 or 95% or 95 over 100. So this is the first probability given to us. I'll put that here. The next thing, it says the probability that it would be detected by device B is 0.98. And the probability that it would be detected by both devices simultaneously is 0.94. So we've been given quite a lot of information. You will see here that I've highlighted them. Some of you don't have that time during the exam to highlight them, but you can look at these as phrases of interest or points of interest in the extract. And I'm going to teach you, if anything, this is a very important skill to be able to, in maths, in physics, in any subject, to divide a complex question into its smaller constituents and then analyze those smaller constituents so that you can get hints from them and a direction as to how to start a question. So it says here the probability that it will be detected by device A is 0.95. So we're going to write here PA is 0.95. And there's another piece of information after this that I will make clear. The probability of it being detected by device B is 0.98. And the third information, both devices simultaneously, this means PA and B. So it would be detected by A and B. Remember, both devices simultaneously means that both of them are detecting them. And we said that intersection, or A and B, it means that both of them or both of the events occur. So both A and B detecting occurs. And this is 0.94 as given to us by the question. Now, here's something that we can do, that we can surmise or come to by using the information in these 2 points. In the points of the green point, or the green highlighted point, and the orange highlighted point. Now, if you can see, and this is quite clear, that both of these probabilities, when you add them together, they are not equal to 1. It means that they are not mutually exclusive. There's obviously other ways that you could come to this conclusion. By just the fact that PA and B is not equal to 0, you can already see that it's not mutually exclusive. But if you can see that if I add two events that are occurring at the same time, or they don't occur at the same time, for example, but if I add two events and they're not equal to 1, so if they are not equal to 1, then it's not mutually exclusive. So what would make this event become mutually exclusive? Maybe if the question said that if detector A doesn't detect the fire, then it would be detector B that detects the fire. Or maybe they say the probability of detector A detecting the fire is 0.6, and that the probability of detector B detecting the fire if A doesn't is 0.4. When you add them together and they equal 1, then you can say, okay, if it's not 1, then it's the other, then that's mutually exclusive. Anyway, as I was saying, this is just a side note. But PA and B not being equal to 0, that is the biggest telltale that this is not mutually exclusive. Let's start with the questions at hand. 4.2.1. If smoke is present, what is the probability that it would be detected by device A or device B or both devices? This is the biggest telltale for us to use what? To use that all known formula. We're going to use that formula PA or B, because they use the words A or B, device A or B is equal to PA plus PB minus PA and B. And we have all of these things and we are ready now to substitute. So you write down the formula first and then we substitute. We want to find out what is PA or B. This is what we want to find out. This is the unknown. And we have this information. PA is equal to 0.95. PB is equal to 0.98. And PA and B is equal to 0.94. This would be equal to 19 plus 9. 8. So let's say 1.83 minus 0.94. So this would be 0.9. 1.09. No, man, it can't be. Let me just use my calculator. Otherwise, I'm gonna lose my mind here. 1.83 minus 0.94. Okay, 0.89. Now, the reason why I sneered and disgusted at 1.09 is because the probability of something cannot be more than 1. You can't be more than certain. You can't be more perfect than perfect. I know that's lies that you might tell in a romantic sense, but you can't be more perfect than perfect. And in this case, you can't be more certain than the number 1 or 100%. Maybe if you're exaggerating. Okay, 0.89, we've got that by looking at the question. We say device A or B or both devices. We use this formula, that was our telltale, and we got our answer. Now the next question, to finish this off, 4.2.2, what is the probability that smoke will not be detected? So the probability that smoke will not be detected, let's go through that. There are different permutations or different circumstances where smoke would not be detected. So for smoke not to be detected, it is either device A didn't detect the smoke, and device B didn't detect, and either one of them didn't detect. So device A didn't, and device B didn't. So all this to say, for smoke not to be detected, A didn't detect it, B didn't detect it, and both of them didn't detect it. So this is a nice, fancy way of saying we want to find the complement of A or B. That's what it's saying. So we want to find the complement of A or B. Firstly, why did I say A or B? That's the first question you might ask. Why did you say A or B, sir? Because A or B means A or B or both. And for smoke not to be detected, it needs to not be detected by A, B, or both. Why did you say complement, sir? And I'll tell you why. Just relax. Don't be so pushy. That's maybe what you're thinking. Why are you saying complement? Because we know the probability of detection. The detection probability is known. So if we say 1 minus the known, we'll find the unknown. So whenever we are talking about two opposite things, now in this case we're talking about detection or no detection. Detection or no detection are natural complements of one another. It is either it detects or it doesn't detect. It's not like there's a middle ground where it's flirting with detection. It's just, I don't know if the sound for detection was wee wee or it's quiet. It's either ew wee wee or it's quiet. It's not wee. There's no middle ground for detection. It's either it detects or it doesn't. So whenever you have a not in your question, assess, is this thing trying to make a polar opposite for my situations? Is it either it detects or doesn't detect? Is it either it's odd or it's even? Is it either it's heads or tails? Then you can see that these are naturally complementary events. So that's why we need to use PA or B. And we're going to use the complement of PA or B as we've said before. So it's going to be 1 minus the probability of A or B. And it's going to be 1 minus 0.89. And this is going to be equal to 0.11. So the probability of the smoke not being detected is going to be equal to 0.11. Guys, that is all for today. I really hope you've enjoyed this. I need to find a way of making these lessons shorter, if they even need to be shorter. If you watch this, because I'm starting out in YouTube, I hardly get comments. But if I do get comments and you think that, look, it's the right duration, sir, you don't need to call me sir. I'm just used to it because I teach part-time at the school. So people normally call me sir. You can call me Mr. K. I'm sorry, I didn't introduce myself. So you can call me Mr. K. And if you need shorter videos, I'll find a way to make that happen. Obviously, when I'm explaining a concept, it might take a bit long, but I hope you've understood this. I hope you've enjoyed this. I hope that it was fruitful for you. And as always, like and subscribe. Share the video to someone who needs to know what is going on with probabilities. Share the video with someone who needs to ask a question. Email me on the... If you go to the channel page, you'll find the email. They email me a question. I'll try to get to you as soon as I can. Have a good day, guys. Bye.